After looking at the velocity triangle, now let's consider the other part of the Pelton wheel or an impulse turbine, that are losses and efficiencies. We know that when we saw the installation drawing or sketch, that the fluid flows from the reservoir higher up, moves through the pipeline, causing some frictions, and this is one of the source for the losses. So from the pipeline up to the nozzle where the jet leaves the pipeline or the nozzle, and it enters or hit the bucket, and then it creates the rotations of the Pelton wheel. Then along the way from the reservoir to the nozzle, we have several losses that creates an efficiency. Now first, let's have a look at the pipeline transmission's efficiency. In here, due to the frictions between fluids and the pipeline, we have the pipeline transmission efficiency, that is the functions of energy at the end of pipeline divided by the energy available at the reservoir. So if we look back at the drawing of the turbine installations, we can write down this efficiency mathematically as transmission efficiency, pipeline transmission efficiency, equal to H1 minus to the power loss due to frictions divided by the energy available at the reservoir. So H1, if we remember this drawing, that is the head available between the reservoir to the center line of the nozzle. Or we know that when energy available at the reservoir, H1 minus to the losses, is equal to H. And as the fluid leaves the pipeline, it will enter the nozzle, and the interactions between the fluid and nozzle will lead us into the nozzle efficiency. That is the functions of energy at the nozzle outlet divided by the energy at the nozzle inlet. At the nozzle outlet, the amount of head is equal to the H prime, and divided by the energy at the nozzle inlet, that is equal to H1 minus HF, or this one is equal to H. And we know that the H prime itself is a function of the absolute velocity to the power of 2 divided by 2 times gravity. So that the nozzle efficiency can be written as given here. The absolute velocity at the inlet to the power of 2 divided by 2 times gravity times the head available at the nozzle inlet. And if we combine the nozzle efficiency multiply with the efficiency of the pipeline transmissions, we have a functions of absolute velocity at the inlet of the nozzle to the power of 2 divided by 2 times gravity times H1, or head available at the reservoir. And if we look at these equations, it is a functions of both efficiencies. And then as we know, as the fluid leaves the nozzle at velocity of C1, there is a chance that we have some losses and so on, or frictions maybe. And we will have nozzle velocity coefficients, or CV, that is equal to C1, or the absolute velocity at the inlet of the bucket, divided by 2 times gravity times H to the power of 0.5. And then by looking at these equations, it is actually the square root of the nozzle efficiency, or we can write down that the nozzle efficiency is equal to the nozzle velocity coefficients to the power of 2. And these are the 4 parameters, or at least it is 3 parameters, or there are 1 parameter that can be written in two different forms. That is the nozzle efficiencies. So nozzle efficiency can be like this, or can be a functions of nozzle velocity coefficient. So we can use these functions of losses and efficiency when we are going to examine the performance of an impulse turbine or Pelton wheel in this case.